Picard here with another geometry lesson. In today's lesson, we'll be talking about ratios and proportions. Ratios and proportions are actually concepts that are typically covered in Algebra 1. But we'll need to use the concepts to do some work in geometry in future lessons, particularly when we talk about a similarity of two shapes. So this is basically a review of some things you've probably covered in the past. First question we might ask is, what is a ratio? What is a ratio? A ratio is a comparison of two numbers by division. So for instance, if I want to compare the numbers 6 and 8, I can write them as a fraction like this, and we could say that's a ratio. Why? Because it's a comparison of the two numbers by division. I can compare any two kinds of numbers with a ratio. So for instance, I could compare decimals, 0.1 and 0.3. Oops, I don't know what happened with the 0.3. I can compare fractions actually with a ratio. This may look a little bit strange, but suppose we had 1/4 compared to 1/2. I can do that. It's a little bit complicated because here we actually have two ratios within a ratio. That might not be fun to deal with, but it's something we can do. I can also compare variables. For instance, x compared to y, or x compared to 9, for instance. So any kind of number you can imagine can be plugged into a ratio for the purpose of comparing it with another number. You can write the ratio of a to b as the quotient a over b when b does not equal 0. As long as b is not equal to 0, you can write it in this form, a over b. Now I want to mention that the order of the variables is important, the order of the values, the order of the numbers. So when we say a to b, a always goes in the numerator. If we say b to a, I want to compare b to a, then we put b in the numerator. Okay? And if we look at this in more of a practical example, suppose I want to compare 12 donuts, excuse the East Coast spelling there, to 18 muffins. I want to compare 12 donuts to 18 muffins. Well, the 12 goes in the numerator and the 18 in the denominator. If I want to compare 18 muffins to 12 donuts, 18 goes in the numerator, 12 goes in the denominator. So again, order matters. I think you can see, by the way, that if we mess up order, then we'll end up with the reciprocal of the number we wanted. If I want to compare, in this case, the donuts to the muffins, but I say 18 over 12, I have the reciprocal of the number I wanted. So that can be a little bit dangerous. Watch out for that. Look at an example here. There's a photo that is 8 inches high and 5 1/3 inches wide, is enlarged to a poster that is 2 feet high and 1 1/3 feet wide. Something like this. We have a photograph on the left and we have a poster on the right. And so I've given the measurements here. The photo is 8 inches high by 5 1/3 inches wide. And the poster is 2 feet high by 1 1/3 feet wide. Now there is a problem we run into here if we want to compare these values, and that problem has to do with the unit labels. Not an impossibility, it's just not very convenient for us. In other words, if I want to compare the 8 inches to the 2 feet, it'd probably be better if we change the 2 feet into a measure in inches. And I think most of us know that 2 feet is equal to 24 inches. 1 1/3 feet equals 16 inches. A foot is 12 inches, and 1/3 of a foot is 4 inches. 12 plus 4 is 16. So now we've got these values in inches, and they're a little bit easier to compare. So suppose the question is asked, what is the ratio of the height of the photo to the height of the poster? The height of the photo, 8 inches, to the height of the poster, 24 inches. There's the ratio. Pretty simple. A couple things we need to take note of. First of all, when we express a ratio, we try to reduce it down. So 8 over 24 can be reduced to 1/3. So that's important to keep in mind. Generally, the correct answer is to reduce it down. Second thing that we need to notice in this particular instance, and I'll write this out a little bit more carefully, 8 inches divided by 24 inches. You'll notice that when we do the unit analysis, and a unit analysis is when we look at the units involved. Here the units are inches. When we do the unit analysis, we find that the units go away. Why is that? Let's talk about that. The reason is because inches divided by inches equals 1. we can actually divide inches by inches, and we find that there's 1 inch per inch. In other words, this becomes somewhat meaningless. It cancels out, to use that language. And so we're left with simply 8/24ths, or quite simply 1/3. In many, many instances, when we compare values in ratios, the unit labels drop away. And so we're left with just a number. It's not 1/3 inches. It's not 1/3 anything. It's simply 1/3. That's the comparison. That's the ratio. Let's ask this question. What is the ratio of the width of the photo to the width of the poster? Remember, this value here was 5 1/3, and this is 16 inches. 5 1/3 inches, 16 inches, sorry. So let's try it again. Let's compare 5 1/3 to 16. We do that. We're talking about a ratio. Ratio is a comparison of two numbers by division. So we know that the width of the photo comes first. So we put that in the numerator. And then, that's inches. And then the width of the poster comes second, 16 inches. All right, this one's a little bit more difficult. In order to clean some of this up, let's look at the unit analysis first. We have inches in the numerator and inches in the denominator, so those cancel. We can get rid of those. And then we'll notice that we've this mixed number in the numerator. You may remember dealing with mixed numbers. In order to deal with mixed numbers, you have to multiply by the denominator. So we're going to multiply both the numerator and the denominator by 3. 5 1/3 times 3 is actually 16. And 3 times 16 is 48. Now, that number is not in simplest form yet. We need to just simplify that a little bit. And you'll notice that 16 goes into 48 3 times. Actually, we saw that happening down here. And so we end up with 1/3. We have exactly the same values with respect to the widths that we had with respect to the heights. And we'll talk about that a little bit more later as we go forward. So that's how we find the ratios of values that are given to us. The thing we need to look at is our proportion. And again, we should probably ask the question, well, what is a proportion? A proportion is very simply a statement that two particular ratios are equal. So as an example, 1/3 equals 2/6. Notice I have a ratio on the left, I have a ratio on the right, and I'm saying that they're equal. Well, that's what a proportion is. So those are equal. Proportions are generally written in a couple forms. This form on the left is very useful for us mathematically. A over B equals C over D. You can see the ratio on the left, ratio on the right. Sometimes we'll find a form like this. A is to B equals C is to D, or A compared to B is equivalent to C being compared to D. You might even see it like this occasionally. A is to B as C is to D. Okay. Sometimes you actually see this in literature questions, maybe on standardized testing. You might see something like this. Hand is to glove as foot is to what? And then you have to fill in the blank, right? Foot is to shoe, foot is to sock, whatever the case may be. Same concept. It's a comparison on two sides of an equal sign. When 3 or more ratios are equal, we can write what's called an extended proportion. As an example, you might see something like this. 6 over 24 is equal to 4 over 16 is equal to 1/4. And the truth about extended proportions is that they can be infinite in length. There's an infinite number of terms that we could put in here. For instance, we might write that that's equal to 3/12, or it's equal to 2/8, etc. So there's an infinite number of terms that we could compare, and we can begin to extend this proportion out. A proportion is generally solved by finding the value of some variable. That's what the tool is useful to us. So if I have a proportion that has a variable in it, that is, I'm trying to compare some different numbers, and I'm trying to find the variable, there are certain ways of actually solving that. How do we solve? Well, we cross multiply. You may remember that to cross multiply, for instance, say we have 2 over 4 equals x over 8. To cross multiply, we take the product here, that's 4x, and we set it equal to the product here, 16. Please notice this is how we solve a proportion. Sometimes people get confused when they're multiplying fractions. For instance, 2/4 times x over 8. They try to cross multiply here and everything goes south. You can't cross multiply here. It doesn't work. Cross multiply across the equal sign to solve proportions. Once you get it to this stage, you just divide by the coefficient and you end up with x equals 4. That's probably what we expected it to be. So we can solve by cross multiplication. We need to ask the question real quick, why does that work? In fact, we have a rule, it's called the cross multiplication theorem, and you know that shortcuts called terms we usually prove. The rule says that let a, b, c, and d be real numbers with b not equal to 0 and d not equal to 0. If a over b equals c over d, there's our proportion, then AD equals BC. There are our cross products, AD and BC. How do we prove it true? Let's take a look. A over B equals C over D. To prove it, I'll just multiply both sides by the product of the denominators. So the denominator is B and D, B on the left, D on the right. Let's multiply by BD, and on the right we'll multiply by BD, and let's see what happens. On the left, when I multiply by BD, I end up with ABD over B. And on the right, I end up with CBD, or BCD, however you want to say it, over D. You can see that the D's cancel on the right side, and the B's cancel on the left, and I am left with AD equals BC. That's why it works. Of course, this is a shortcut. Remember that the shortcut works no matter how complex the problem. If I have something that looks like this, A plus 2 over 16 equals A minus 8 over 20. I can still use the cross multiplication theorem. I simply multiply this binomial by this constant, and I set it equal to this binomial times this constant, right? Cross products here, 20 times A plus 2, and then I just begin to solve it like I would any other algebra problem. We need to look at a few corollaries to cross multiplication theorem. Corollaries, remember, are shortcuts to shortcuts. They're the extensions of the shortcuts that we learn. When we look at this proportion, A over B equals C over D, we can find and be sure that it's equivalent to the following statement. Number one, we find that it's equivalent to B over A equals D over C. What happened there? How did we get from this proportion to this one? That's the question. I think you can see quite simply that we just flipped over both of the ratios. Okay, we just flipped them upside down. And that's perfectly fine. In fact, if you look at the cross products on the bottom here, that is number one, you see that CB is equal to AD, and you can see that's exactly the products we have when we do the cross products up here. AD equals CB. Same cross products, they certainly must both be true. Let's just see if we can find a mathematical way to get there. If we start with A over B equals C over D, notice again that we can multiply both sides by BD. And we know, we've already gone through this, that we end up with AD equals BC. Now, in order to get to this, B over A equals D over C, all we need to do is divide both sides by A. That cancels. And then divide both sides by C. So what we end up with is D over C is equal to, these C's cancel, B over A. So we find that that's true. Let's look at the next one. In order to discuss what happens here, I need to introduce a couple terms. In order to make those terms a little easier to remember, I'll write the proportion A is to B equals C is to D this way, something we looked at a few minutes ago. When I look at the proportion written this way, these two terms in the middle are called means. Call those the means of the proportion. These terms on the outside are called the extremes. Means and the extremes. Think about the extremes as being outside, far away. Think about the means as being in the middle. That word means, by the way, hopefully it's something that you've heard, at least the word mean, singular. When you study measures of central tendency in algebra, mean, median, average, mode, these terms, notice it has a similar sense to it. There's something about being in the middle. And when we look at this proportion, we find that B and C are in fact in the middle. We call them the means. There's a more technical mathematical reason for calling them the means, but this is easy to remember. So what's happening over here? Let's take a look at number 2 here. If we ask the question, well, what happened? How is number 2 different than the original? What changed? What was moved around? You can see that the A and the D are still in the same position. A and D are still in the same position. But you can see that the B and the C have switched. They've switched positions, B and C. What does that mean for us? It means quite simply that in a proportion, you can switch the means without changing the truth of the statement. So if I have A over B equals C over D, I can switch the means and it becomes A over C equals B over D, and it's still true every single time. Let's take a look at a practical example. 1/4 equals 2/8. We all know that that's true. Let's see what happens when we switch the means. 1/2 equals 4/8. Still true? Of course it is. We can always switch the means of a true proportion. Let's talk quickly about why that's true. Again, we know that if we have A over B equals C over D, that is equivalent to AD equals BC. And if we perform some basic operations, divide by C, C's cancel. Divide by D, D's cancel. We're left with AC, A over C rather, is equal to B over D. And so sure enough, with a little bit of algebra, we get there. Okay. So we can flip proportions upside down. We can switch the means. What else can we do? Hopefully we can see that if we were to take this and flip it over, we'd have C over A is equal to D over B, which means we can do a combination of things. We can switch the means and then flip it over. That's still true. We can actually switch the extremes. So if I start with A over B equals C over D, I can turn that into D over B equals C over A. That's fine. We can switch the extremes. We can switch the means. We can flip the thing over. And what are some things we can't do? Well, we can't just switch a mean with an extreme. That does not work. We cannot take and say that A over B is equal to D over C. That is not correct. So be careful about that. We can switch the means, switch the extremes, flip the whole thing over. We can't just flip a piece of it. Okay? Likewise, we cannot say that A over D equals C over B. What happened there? I switched an extreme with a mean right there. That doesn't work. Can't do that. Anything else we can do with a proportion? Yes, one final thing we need to look at. If A over B is equal to C over D, then A plus B over B is equal to C plus D over D. Where did that come from? Let's take a look at that one. Remember that any number divided by itself is equal to 1. So B over B equals 1. D over D, or divided by D, equals 1. Which means, by the transitive property, B over B equals D over D. That's an important concept. One of the things it allows us to do is, while maintaining the addition property of equality, I could add B over B to the side of one side of an equation, while I add D over D to the other side. Perfectly fine. So suppose I had the following equation: A over B equals C over D. I can actually add B over B to the left, while I add D over D to the right. And that's perfectly fine, because really all I'm doing is adding 1 on the left and 1 on the right. Well, now we have a situation in which we have fractions on the left that are being added together with the same denominator, common denominator, and on the right are being added together with a common denominator. And you may remember that when I add fractions with common denominator, I simply add the numerators and set them over that common denominator. So this turns into A plus B over B equals C plus D over D. So again, this is perfectly fine. This is a legitimate form of the original proportion. Quick review one last time. When I have a given proportion, I can flip the whole thing upside down, meaning I can flip both sides. I can switch the means, or I could switch the extremes. Either one would be fine. I can also add the denominator on each side to the respective numerator, and that's perfectly fine. The thing we need to look at is this idea of scale drawings. Most of us are familiar with scale drawings. We see them in maps, we see them in diagrams, all kinds of pictures that people come up with. In a scale drawing, the scale compares each length in the drawing to the actual length in real life. Here's an example. We have a diagram of a portion of a house. Maybe it's an entire house. There are 4 rooms shown in a hallway. And down the bottom here, there's something called a scale. And the scale says that 1 inch in the diagram is equal to 16 feet in real life. What does that mean exactly? Well, let's take an example here. If we were to measure this diagram and we found that this is actually 1 inch in the diagram, that means that in real life, it's actually 16 feet across the living room. If we measure this and find it to be 2 inches, then in real life, the living room is actually 32 feet long, or 32 feet across in that direction. So we can use the scale on the diagram to determine the actual lengths in real life. It actually comes quite handy when we're trying to work with maps. We can look at a map, we can use the scale to find out the exact distance between 2 points in real life based on the distance on the map. Anytime you look at a map, you should see a scale somewhere on the page that shows you what the actual scale is, a representation of the values. That's everything we need to talk about here, talking about ratios and proportions. Remember, it's important that you take the time to work through some problems on your own. If you have any questions, as always, please send me an email.